Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Sodium acetylide, NaC CH, is a strong nucleophile and base. When it reacts with a ketone, nucleophilic addition, the acetylide anion attacks the electrophilic carbonyl carbon. Moving on to the next step. Identify the electrophile. Cyclohexanone has a carbonyl, C is equal to O, at C1. The carbonyl carbon is electrophilic. Moving on to the next step. Nucleophilic addition of acetylide. The acetylide ion, HCC, attacks the carbonyl carbon of cyclohexanone in a nucleophilic addition reaction. This breaks the C is equal to O pi bond, and the oxygen becomes an alkoxide anion. The acetylide carbon forms a new C to C bond with the former carbonyl carbon. And for the final step, protonation. Treatment with H2O and H+. Step 2. Protonates the alkoxide to give a tertiary alcohol. Product identification. The product is 1-ethylcyclohexane 1-ol, a cyclohexane ring with both an OH group and a CCH, ethynyl, group on C1. This is a tertiary propargylic alcohol. This matches option C. Why other options fail? A. Shows a cyclohexanone with an ethynyl group alpha to the carbonyl. This would be an alpha-alkylation product, not a nucleophilic addition to the carbonyl. Sodium acetylide under these conditions performs 1-2 addition to the carbonyl, not alpha substitution. B. Shows an allylic alcohol, cyclohexanol, which would require elimination or a different reaction pathway. Not consistent with acetylide addition to a simple ketone. D. Shows 1,1-diethylcyclohexane with 2 ethynyl groups and no of this would require 2 equivalents of acetylide and loss of oxygen, which does not occur under these conditions. Therefore, the correct answer is C. Therefore, the correct answer is option C.